Hello, everybody. Today we will go over our third lecture in this particular series of linear algebra. And here I will like to explain a particular topic that is confusing in the mind of many of our students. And it was when I was taking linear algebra, because our first introduction to this word vector happens when we are taking the physics course in our 10th grade, where specifically we are told that there are some scalar quantities, there are some vector quantities, like we have acceleration, momentum, force. We call them vector quantities because they have a magnitude, the intensity of that particular force, and it has a direction associated with it, northwest, pushing or pulling. So all those concepts are there. But now when we go to higher classes in linear algebra, we also come across this. But before we that, we take this first course in programming, and in this particular programming course, we also come across this notion of vector, where the vector means an ordered list of numbers. So as you know, that list is a particular data structure. We also have arrays as a data structure. Then we have linked list and all those concepts. So this is being introduced in our first course in programming. So here in programming, when we talk about vectors, we mean an ordered list, which is a one-dimensional list, like it's a one column. I will not say one dimensional, I will say one column. So it's a top to bottom, just like a tower. So if the numbers are represented in towers, then they are called vectors. Or if I'm in the programming paradigm or programming domain, I will call it vectors, list of numbers. So list is an ordered list. Here the position of one and the position of two is important. They have to be at these positions. If I change their position, like I take the two and put it on top, and one I put it on the bottom, then basically that will not be the same vector as it was before. So the order here matters. That's why I says ordered list of numbers. So in linear algebra, we also are being introduced when we go to our, let's say, second year of this engineering or science program. We are introduced to vectors again, but this time vectors are in a mathematics course like linear algebra. So in linear algebra, the notion of vector is something that acts as a bridge between the physics concept of the vectors and the what we call the ordered list concept of the computer science domain. So it comes right in the middle. Whereas in mathematics, we say that all the ordered list of numbers can represent a particular arrow, okay? But this arrow is the same as in physics. So it can represent an arrow, but it is a special type of arrow, because the arrow that is representing that ordered list of numbers is actually fixed, and it is fixed right at the origin. So it's a position vector. So basically it represents it cannot move around in space. Just like in physics, as far as the magnitude and direction is constant, that arrow can move. But this is not true in case of linear algebra. So in linear algebra, we also have a vector. On one hand, it is an ordered list of numbers. It is a column, but that particular ordered list of numbers can represent an arrow, but one end of the arrow has to be fixed at the origin of our coordinate system. Okay, so I will just show you the way it has been shown in this particular UPhone, sorry, this YouTube video, and you can see that. So for example, here it shows that we have a house. And when we talk about house, it has two features. One feature of the house is the area of the house. So it's a square footage, 2,600 square foot. And on the other hand, this house has another feature, which is the price. But keep in mind, these two features basically are associated with the same house. So in order to describe these two features, I will use an ordered list of numbers and I will put them as a vector. Now you can see that I put 2,600 square foot on the top. I put $300,000 on the bottom. But I'm not going to mix them. They will remain separated. These two numbers will remain separated. I will not mix them because this one is dollars and this one is square foot. Of course, the units are different and they are not the same thing. So I cannot add them. So they will remain separated. But I want to enclose them in the square bracket just to make them something that represent one particular house, one object. So because they are features of one object, so I put them in one square bracket. So it might be some other feature like color of the house is yellow color. I put yellow on the bottom here, and it will have now three components, and I will call that particular vector belong to a R cube three-dimensional space. This particular vector contains two components and it belongs to R2, which is a two-dimensional space. So keep in mind that the vectors that we see in linear algebra, basically they are an ordered list of features for one particular physical object, okay? But on the other hand, we want to graphically represent this. So we will be making use of arrows, the way the arrows are being used in physics. But now we have to link them. So here it is, the way we are linking them. We are linking the concept of vectors, which is an ordered list of numbers in computer science, with the concept in physics. And we are linking them through this position vector concept. So we say that an ordered list is a vector and it can be represented with an arrow as far as the one end of the arrow, which is the tail end, should be fixed at the origin. So if it is fixed at the origin, then it becomes a vector for linear algebra that can represent an ordered list of numbers. Okay. So I will just show you. Now the most important things that we are more concerned in linear algebra is that vector is added to another vector. So the way we show it in the books, we put a boldface alphabet and we put a small arrow on top of it. And we have another vector W and we put an arrow on top of it. So these V and W becomes two vectors. So the most important notion is vector addition. So how one vector is added to another vector. Here, once we make this a position vector, then their addition become easier. Their addition become exactly same as the rules we learned in our physics class, that one vector can be added to another vector to make a resultant vector by head to tail rule. So if you can see here is head to tail rule. So the first vector and the next vector starts from where the first vector ends and extends in the same direction. And then the resultant is starting from the tail of the first towards the head of the second. So this one, the one where I put my arrow, my arrow traces this particular vector is the resultant vector. There is another very special operation that we usually encounter in linear algebra a lot, is scalar multiplication or scalar multiple of a vector. What is scalar multiple of vector? It means some number is multiplied with a vector. When a number is multiplied with a vector, the graphical effect of it is that the vector does not change the direction, only its length become extended depending on the number by whom you are multiplying that particular vector. So if you multiply it with a 2, the length will become double. If you multiply it with a 3, the length become triple. Similarly, if you multiply it by 1/2, then the original length will become half, but the direction will remain same. But on the other hand, if you multiply it with some negative number, like if I multiply it with -2, then it means that that particular vector will be extended, okay, and then it will be reflected in a sense that its arrow will change the direction. Now the arrow direction will be downward, okay. So these both notions are exactly same, as these notion can be easily applied to this concept of ordered list. So let's say we have two ordered lists. So we have a V vector and we have a W. If you add them, you will add them just like you were adding an ordered pair of numbers. 3 will be added to 2. 3 cannot be added to 1. You cannot violate the order. And -5 will be added to 1. This -5 cannot go and move across and be interacting with the 2. No. So in this case, we will also get the addition as another vector which will have two components, the same as their original components from whom they made from. Now, if you multiply an ordered list with a number, because we said that in linear algebra, the vector actually represent an ordered list, and at the same time it represents a position vector. But if I consider it as an ordered list of numbers, then if you see that this 2 will be multiplied with the 3, and this 2 will be multiplied with -5. So it will be 6 on the top and -10 on the bottom. So it the, the scalar multiple means that you multiply a number with each component of the vector. So this is a scalar multiple of a vector. But keep in mind, it has a graphical aspect. And the graphical aspect is that if it is an arrow, if you multiply it with a 2, the arrow will be extended. If it is -2, the arrow will be extended and then flipped. So let's look into this and try to understand what is the meaning of it. So for example, when I say, now if you look into this situation, if I say I have a vector -2 and 3, okay, it is enclosed in a square bracket. So this is in linear algebra. So in linear algebra, when I tell you that I have a vector which has components -2 and 3. So if you look at these two components, basically, if you want to graphically represent this vector in linear algebra, you will represent it by an arrow. But the only difference between this arrow and the physics arrow is the physics arrow can move in the space, but here, this particular arrow is stuck. Its tail is stuck on the origin. So you will have a coordinate system, x-axis, y-axis, and right in the middle you have origin. So the tail of the arrow will always be at the origin in case of linear algebra. And the head can be dictated by these two components. So when we say -2, 3, it means that on x-axis, I moved 2 units towards the left, and 3 means, the bottom 3 means that I moved 3 units on the y-axis. So 1 unit, 2 units, 3, and I will end up in a position where I will put the arrow. So now if I join this position with the bottom, I get an arrow, the same arrow that we see in physics, okay? But this time, this arrow is representing an ordered list of numbers rather than magnitude and direction. So this is the difference here. But the same properties that we learned in physics will apply here. So this type of representation is used in linear algebra. So in linear algebra, when we say a vector, we always means a position vector, which can be completely determined by these two numbers, the numbers that we put as an ordered list. So now, let us say I have another one. I'm just So you see, here I have another vector, -2 and -1.5. So -2 means it moves along the x-axis 2 units, and then it moves, -1.5 means that it moved downward on y-axis because of this negative sign. And wherever it end up, we put an arrow, and this arrow is starting from the origin and move towards the endpoint. And this arrow is a graphical representation of the vectors in linear algebra. Similarly, we can have three-dimensional vectors in linear algebra. Three-dimensional vector means three ordered list of numbers. So we have a square brackets in which we put three numbers. But keep in mind, we have to keep them separated. We cannot mix them. So 2 is on the top, 1 is on the bottom, 3. So these are three different numbers, and they are ordered numbers. It means that their position is important. I cannot mess up with their position. I cannot randomly put their position. And now, according to our new graphical method, this 2 minus 3, sorry, this 2, 1, and 3, this particular vector represents an arrow, but that arrow has to start from the origin. So what we have is right here, if you see very clearly, that we moved, now we have three axes because we are talking about three-dimensional vector. So three-dimensional vector can only exist in a three-dimensional space. And three-dimensional space is always represented with three axes: x-axis, y-axis, and z-axis. So here is your x-axis, here is your y-axis, and the upward arrow is your z-axis. Now on this x-axis, on the positive side, we move 2 units. So we come here where I put my arrow, my computer mouse arrow, okay? And now I moved along the y-axis 1 unit. So this red one representing, I'm moving along the y-axis. And then I have to go up 3 units, so 1, 2, and 3. So ultimately I reach, now wherever I reach after making these 3 movements, 2 along the x-axis, 1 along the y-axis, and 3 units along the z-axis. Wherever I reach after making these 3 movements, that is my end point where I have to put the arrow. But you should keep in mind that the beginning of that arrow, the initial point of the arrow is at the origin. So you will pick an arrow and you will start from the origin and you will move to this final point. This particular arrow is representing now this vector, this order list of 2 minus 3. So this 2 minus 3 is represented by that vector. So if I can just show you a little bit more movement, you can see it very clearly. You see? So every triplet of number is represented by this particular arrow, okay? And now I wanted to show you what happens once you have 2 vectors, okay? Once you have 2 vectors, V and W. Now keep in mind these 2 vectors, every vector is starting from the origin. It means that these 2 vectors are our linear algebra vectors. These arrows are actually representing our linear algebra vectors. They are in some way not related to what the physics is, but because we have represented by the arrows, so we can use all the physics vector algebra, okay? So here is V, it starts from the origin, goes towards this final point. We have a W, which starts again from the origin and moves toward this point. Now, if I say I want to add them, so I will add them like this. So I will take my W and I will put it wherever the end of the first vector is, and I will start from here, move it parallel to my original W, and wherever it ends, I will start this resultant vector. So this V plus W is a resultant vector, which is a vector addition of V and W. So this notion is exactly the same as we done already in our 10th grade physics class. But here, the most important thing is you have to start from the origin. So here the origin of the coordinate system plays a very significant role. Okay. And now I will just show you how you have an ordered list of numbers. So if you have a linear algebra, and if you have a vector 1, 2, and you have another vector 3, -1, and you want to add them, because most of the time in linear algebra, we will come across this addition of vectors and then scalar multiplication. So if you have addition of two vectors, but keep in mind, when we talk about two vectors, these vectors actually means ordered list of numbers. So it's a column. It's just a column. So you have one column here and you have another column here. These columns are added. So the first column, okay, 1, 2 is represented by this yellow arrow. But keep in mind, this yellow arrow is starting from the origin. Similarly, you have 3, -1. This is again another vector. It always starts from the origin. So here it is. If you look at my arrow, here it is. But in order to add them, I will pick this and I put it according to head and tail rule that we learned in physics. And then I put them here, and you can see it that after. Now you can see it very clearly that when these two are added, I'm getting this resultant arrow. But keep in mind, this resultant error, wherever it ends up, it can also represent the addition of this ordered list pairs. So 1 plus 3 is giving you 4. So 1 plus 3 is actually on the x-axis, you have a 1, and then you have a 3. And on the y-axis, you have a 2 and -1. So you go up 2 and then you come back because of -1. You come back and you end up right here. So the addition, the way we do it in programming for the ordered list, is going with our graphical way of vector addition. So keep in mind these both are equal operation in some sense, that one corresponds to the same. So we can go from arrows to the ordered list of numbers, and from the ordered list we can come back to arrows. So they both are representing each other. So this is a very nice thing, and this is a graphical visualization that will help you a lot during that particular course. Okay. Similarly, if I have to multiply, which we call them scalar multiplication, okay, the scalar multiplication of a vector, it also comes quite frequently in linear algebra. So if this comes, then this basically means that you have a vector v and you multiply it with some number, which we call them scalars. When you multiply a number, it actually extends it all the way up in the same direction. So it does not change the direction. Only thing it does is that it extends the length of the vector. But keep in mind, the vector has to start from the origin if it has to be in linear algebra domain. Okay. Similarly, if I want to do it 1/3 times the vector. So now here I'm trying to reduce the length of the vector. So the vector originally was here, it become 1/3 smaller. The arrow direction hasn't changed, but its length has been changed. Similarly, if I wanted to change with the minus, so it will go, it was here, but because of the negative numbers multiplication, it moves exactly in 180 degrees opposite. So it goes flipped and completely move in other direction. Okay. So this is how the notion of two vectors is. So for example, when I do a scalar multiple of this vector 3, 1, it becomes 6, 2. But keep in mind, graphically, it means that you have extended this vector in the same direction. This is same as saying, I have taken an ordered list of numbers and multiplied with the 2. So same notion, okay? So right now in this particular video, we have shown you from this YouTube nice video that basically this particular operation of vectors is a bridge between the concept of vectors that we seen in our physics class and the one we see in our computer science or programming classes. So the arrows can represent an ordered list of numbers as far as they are rooted at the origin. Their root should be at the origin. जिसे हम अपनी ज़बान में कहते हैं जड़ उसकी जो है वो origin. So if their root is at the origin, then that vector is basically the same as the one in the physics. Okay. So now I will show you basically another graphical representation, another nice video that I find out, I searched on the YouTube, which talk about what is this AX equal to B in the graphical world. So AX equal to B, what it represents graphically, what is the geometry behind it? Geometry of AX equal to B, because this visualization of AX equal to B will help you when you will be solving AX equal to B. So I want to show you, before we embark on solving AX equal to B, I want to show you how AX equal to B look like in the geometry, in the graphical sense. Okay, so here it is. You have a system of linear equation, and these are three linear equations. Okay, but keep in mind these are linear equations because the exponents of x is 1, exponent of y is 1, and exponent of z is 1. So these are three linear equations in three unknown, and x, y, and z are unknown. Okay, so we can easily convert this linear system of equation into our AX equal to B. Here they are representing B with V, but keep in mind this is the same thing, that you have a matrix vector product which actually end up into another vector. So you have A times X equal to B. In this case, our B is this minus 302. So B is a vector because here it is an ordered list of numbers, but this B is a three-dimensional vector. So if I want to represent it by an arrow, I will need three axes: x-axis, y-axis, and z-axis. In this axis, it will be an arrow whose tail will be at the origin, and we will extend it somewhere where we will have -3 movement along the x-axis, 0 movement along the y-axis, and then 2 units movement along the z. Wherever I end, this is my end point, and I will pull this arrowhead right there, and I will have a vector that extends from origin till this point, and this will be representing B. So that will be my B, which is represented here as B. Okay. A is a coefficient matrix. And you can see this 2 is coming from here, 5 is coming from here, 3, 4, 0, 8, 1, 3, 0. So all these are coefficients of these numbers. And x, y, z, this is also a vector. So if you look into this AX equal to B in the graphical sense, where we can represent these x and B, both vectors in a coordinate system. So if I represent x and y in a three-dimensional coordinate system, both x is a vector which will also have three components, and it will be a vector whose tail will be rooted at the origin. B will also be a vector whose tail will be rooted at the origin. And then what A is doing, what basically A is doing is actually moving your x vector on top of this B vector. So let me show you that. And that's very strange. So when you say, and let me run this movie. You see, because of A, what happened that it is taking this vector, which is represented here, x, and move it on top of this green one, which is your B vector. B is represented by V here. So you see, if I just do it again. I will stop it. So when you solve ax equal to b, in the graphical sense, what is going to happen is that you have vector x and you have vector v. You are trying to move this x vector and move it such that the x and v are aligned. So x go on top of v. So when a is multiplied with x, basically it transforms this x vector into a v vector. So A can be represented as a transformation because we are in linear algebra. So it's a linear transformation of X on top of V. Okay. And so in other words, when we are solving AX equal to V or AX equal to B, basically what we are trying to say that we are looking for that X when it is multiplied with this particular coefficient matrix, it will transform it into our B. So can we find that particular X vector? If we can find, then we have solved the problem. So AX equal to B problem, which is the main problem in linear algebra, is basically coming from this notion that can I transform my unknown vector XY into V vector using A. So A is the transformation. Can I do this? And when I do the inverse, so let's say, you see, after applying the transformation, what happens? Your X become extended and get on top of V. So now X and V become exactly same. Okay, so you're looking for that X on which if you apply A, it will transform it to become your final destination, which is B or V in this sense. Okay. And when we are doing, so when you are doing this X equal to A inverse B, what actually means is that you are doing this inverse transformation on B because you don't know X. So in order to find X, you have to bring A to the other side. When you bring A to the other side, it will become A inverse. So A inverse time B means that you are multiplying an inverse matrix, which is an inverse linear transformation, which is moving B back to its original position X. So when it moves B back to original position X, you find the X. So, but keep in mind, this is a transformation. Your arrows are transformed. There is an arrow which is called X. There is an arrow which is called B or V. And we know B, but we don't know X. To find X, what we do, we multiply B with A inverse, which moves it back. It rotates it and it also extends it or compress it, whatever it does. It will bring this B on top of X because of A inverse. And once it becomes on top of it, then it means that you find that X. So you know what the X is. So unknowns are found. And this is the notion behind AX equal to B. So here I will stop this video, and I hope that you enjoyed the video. If you have any question, please send me your comments. You can send me the comments underneath this video, or you can send me the comments on the Google Class for all my students. So thank you very much, and I will just stop my